I welcome all of you for our look at valency bond theory to explain the bonding in complexes. This is the theory that can explain magnetic nature of complexes unlike your Werner's theory. This is based on some presumptions or some postulates like each metal offers as many empty hybrid orbitals as is its coordination number. The coordination number 2 means sp hybrid orbitals and 3 means sp2. 4 can indicate sp3d, sp2 or sp2d. 5 can indicate either sp3d or dsp3. 6 can indicate d2 sp3 or sp3 d2. d2 sp3 means if 3d orbitals are there, it will be 4s 4p. And sp3 d2 means 4s 4p 4d. It means all the orbitals will have same principal quantum number. Here the d will have n minus 1 principal quantum number, s and p will have n. Now let us see. The type of empty hybrid orbitals offered depends on the electronic configuration of metal or metal ion. The type of metal, it can be d block, 3d series, 4d series, 5d series, lanthanide, pi block metal, the type of metal. Nature of ligands. Ligands are of two types like strong field ligands which can influence the electronic configuration of the central metal and its hybridized state. And the weak field ligands which cannot influence the electronic configuration of central metal and its electronic configuration. Now the Cl minus appears to be something special, like it acts like a weak field ligand for 3d series metals like nickel plus 2. It acts like a strong field ligand for 5d 6d series metals like platinum plus 2. Now let us consider the case of cobalt. Cobalt atomic number 27, as we have seen in previous video, its electronic configuration is argon 3d7 4s2, 3d7 4s2, and this is of course 4p orbital 4d orbital. Now when the cobalt is losing 3 electrons, it will be losing the 4s electrons, and also I have indicated A, B, C, D, E, F, G. C electrons will be eliminated from F or G because they are paired. So anyway, now I got cobalt plus 3 with the 3d6 configuration. Now if I am placing it in a field of fluoride ions, fluoride is a weak field ligand, so fluoride cannot influence the d electron configuration. The coordination number 6 is realized by 6 hybrid orbitals formed by intermixing of 4s, 4p and 4d. It is sp3d2 hybrid orbitals, and these sp3d2 hybrid orbitals are octahedral in shape, and I am getting a COF6 3 minus ion, hexafluorocobaltate ion. This is octahedral and it is paramagnetic due to 4 unpaired electrons. Now instead of the fluoride ion, suppose I have say ammonia molecules. Ammonia is a strong field ligand, so it can push these electrons, namely the d and e electrons are pushed in, so that I am now getting 2 empty 3d orbitals and they will combine with sp3. You can get d2 sp3, again that is octahedral in shape, and again I got the complex CO NH3 taken 6 times, octahedral complex only, but this complex ion has no unpaired electrons, hence it is diamagnetic. Have you noticed? So the magnetic nature varies depending on the nature of ligands. Let us also see some other example. Iron atomic number 26 can be 3d6 4s2 as per our previous video. Iron plus 3 is having 3d5 configuration. Now if I am using a weak field ligand like fluoride ions, they don't influence this configuration, so I can get again this sp3d2. This is octahedral complex, all the 5 unpaired electrons are intact, so it is paramagnetic due to 5 unpaired electrons. However, if I am putting cyanide ions, which is a strong field ligand that can push the d and e inside, so AE, D, BD I get, the C only unpaired electron. Now this D and the sp3 combine to give dt sp3 hybrid orbitals. Again I got an octahedral complex, but it has only 1 unpaired electron, that is still paramagnetic. Now similarly I look at manganese. Manganese is 3d5 4s2. When manganese is making plus 3 ion, it is getting 4 unpaired electrons. And now this manganese plus 3 can combine with again weak field ligand like fluoride ion, which has no influence on this electron configuration. So I am getting the hybridization like sp3d2, that is octahedral, paramagnetic due to all 4 unpaired electrons. However, if I am putting a ligand like ammonia, again I will be getting a octahedral complex, but this ammonia strong field ligand will push this d electron inside to give me AD. Only BC2 unpaired electrons are left. The 3D, the 4s and the 4p will combine to get me D2sp3 hybridization, which is paramagnetic only due to 2 unpaired electrons. Now let us extend our discussion to nickel. Nickel in atomic state is 28, configuration 3D8,4s2. This nickel in atomic state itself can combine with carbon monoxide. If there is enough carbon monoxide, now the carbon monoxide being a strong field ligand will push these AB4s electrons into 3D. Therefore, I am getting the empty 4s and sp3 hybrid orbitals. Nickel will make nickel tetracarbonyl, which is tetrahedral, and which is of course no unpaired electrons, so diamagnetic. The same nickel in the form of Na plus 2 ion. Na plus 2 ion has 3D8 configuration, because from 3D8 4s2 you removed 4s2. So the 3D8 is something like this, no? 1, 2, 3, 4, 5, 6, 7, 8. The 3D8, if there are simple chloride ions, this chloride is a weak field ligand, cannot influence the 3D orbitals of nickel. So the coordination number 4 is realized by 4 sp3 hybrid orbitals, 4s, 4p. That is tetrahedral, and that is paramagnetic due to 2 unpaired electrons. However, if there is a strong field ligand like cyanide, it can push the 3D electrons and it can generate a empty d orbital 3D. The d and sp2 will combine to give me dsp2 hybrid orbitals, which are square planar. Therefore, I am getting nickel tetracyanonickelate complex, which is square planar and which has no unpaired electrons, diamagnetic. Notice that the chloride ion can act like a weak field ligand for nickel. For platinum, it can act like a strong field ligand. So it can, instead of sp3, generate dsp2 here. So tetrachloroplatinate is square planar. This valency bond theory suffers from too many assumptions, and so many complications will arise in this theory. So it cannot be rigorously applied to explain the color as well. Hence we have better theory called crystal field theory, molecular orbital theory, which we discuss in probably next videos. Also notice CuNH3 taken 4 times tetraamine copper complex, the hybridized state is often a matter of controversy. Latest research has shown that actually this tetraamine copper complex is not a it is not having coordination number 4. In fact, it exists like diaqua tetraamine copper complex. Here, the hybridized state is found to be, as per latest research, sp3d2, and the 4 ammonias are directed to corners of a regular square plane, and the water molecules are very far off due to something called as John Teller's effect, which we don't discuss now. But if you ignore these 2 waters, it appears like square planar, and copper plus 2 is paramagnetic due to 1 unpaired electron. This is a note on that. Anyway, we will be meeting in next video and discuss about the other theories. Thank you.